So this warm-up problem, if we get time, then we can discuss this at the end. It's not really exactly related to the topic. It's just a nice problem. So I thought. Uh, so you guys can see my screen, right?
Yeah.
So our topic will be coloring arguments. The first part of the talk will be on tilings. Like you have a board and you're supposed to tile it with different uh, shapes of. You're supposed to tile it with some sort of mini boards with different shapes. Like they're called tiles. Uh, that's the first part, and then the second part it's sort of like a problem solving section on combinatorics. It has a surface. The question itself has some coloring in it. It doesn't exactly require any coloring, but I guess it's a psychology. Uh, so this is the first question. I guess it's you have a chessboard, 8 into 8 chessboard, and you remove the top right corner and the bottom left corner. The squares, the top right square and the bottom left square, and you're left with 62 squares. And you want to tile it with dominoes, and a domino looks like a 2 into 1 square or a 1 into 2 square. Is there anyone who has not seen this question? Uh, okay, is there anyone who has seen this question?
Yes.
Uh, so it's like pretty famous, and I guess everyone knows that I said chessboard on purpose, and we just color it black and white. Uh, so if we color it black and white, then the corners, there'll be like the number of white squares and the number of black squares won't be equal. So we can't tile it with dominoes, since a domino covers equal number of white and black squares. So this is pretty famous, but you might be wondering, how did you think about uh, coloring it like a chessboard? Uh, so there are two ways of thinking about it. One is that you just formalize it as a strategy, that you color whenever you have a coloring problem, you just color the board as a chessboard. As you'll see, this doesn't always work, but it's a nice general tactic. Uh, so yeah, yeah, it's pretty famous. So, you guys can try this question for 5 minutes. It's related to the okay. There's no point of just telling. So uh, y- yeah, I guess it's in mathematics. So you can try this for 5 minutes. We'll discuss the. I'll just give hints mainly, and most probably we'll be able to do it with the. It's both 1 into 2 and 2 into 1 dominoes. No, a domino is 1 into 2, as far as I remember. Always. No, a 1 into 1 is generally called a unit square. Yes, we need to the question asks whether or not this picture can be covered with 1 into 2 dominoes. Is that clear? Some okay. Uh, you claim that it can be. Can you show how? Okay, it's straightforward. Can you show how? Yeah, only with 1 into 2. Yeah, can you show how it's Samir, since you say that it can? Uh, wait, just place it how exactly? Uh, just, can you see my cursor? Yeah, so if you place it like this, then this. Just tell me how do you place it? There are many places where you can place it. You can also unmute if that's easier. Yeah, sure. If anyone else has an idea, they can also share. Yeah, I see a message. How many can block the middle part? One is in the middle and the other is, yeah, that's a, you guys can hear me, right? It's showing that my internet connection is unstable. Okay, I hope that you can hear me. Am I audible? Yeah, okay. So, Martin's idea is nice, but just clearing it up front, you could try to tell it, but I guess someone must have messed up somewhere because I think you can't tell it. There's a proof for it. So, uh, we'll just so it's not that easy. Martin's idea is nice. Yeah, he says that I mean it's an intuitive notion. We could think of it like either a dominant. Everyone can see my cursor. Yes, Martin got it actually. Yeah. So Martin's initial idea was that you place. There are two possibilities of placing a tile. It's either in the bridge. Uh, I guess it's clear what a bridge is. So if does everyone get what a bridge is in my definition? The middle parts, this and this. So if so, a domino can be placed either like this or like this uh, for this part or like this. So then you can just that's an idea, and then there's also a way to finish using that, but I guess the coloring proof is a bit easier. You just color it black and white in the chessboard fashion, then you get then you can actually make, I guess we won't get 13 black, 1 white immediately. But there are few cases. So if one domino is placed like this and the other is like this, then we have actually basically separated the two big 5 into 5 squares. So that is not possible to tell individually because 5 into 5 is 25 and that is not divisible. So some domino must be placed in the middle like this or like this, and then tiling just finishes it. It's just chessboard coloring. So the main idea was just chessboard coloring, and so uh, it makes sense to uh, it makes sense many times to just color it like a chessboard and hope that things work. Uh, uh, so this is all well and fine, but coloring arguments generally go much deeper than just chessboard coloring. Uh, so in general, we should just think about uh, uh, where our intuition came from. So here we had tiles, and each tile cover. It would be nice to have a coloring so that each tile covers one square of each type. So a type is easy to define using a color. It's possible to do it obviously using a number, using binaries and stuff like that. But I guess I feel that coloring is maybe a bit more motivating. Uh, so in general, in contests, you would probably use numbers instead of colors because I guess some of them don't allow colors. So that's the deeper idea. And as I just said, the chessboard idea is still pretty nice to me because it works, and you don't want to think about it over and over again about if you have dominoes, then what coloring should I do? Yeah, so this is a nice problem. Can a 10 into 10 board be tiled with T tetrominoes? So a T tetromino looks like this here in the left. And we want to tile this 10 into 10 board with T tetromino. So obviously it's a valid question because T determinants have 4 squares and a 10 into 10 board will have 100. So we should be able to technically tile it with 25 T determinants. Uh, but yeah, you need to either find a construction or give me a contradiction. So I'll give 5-6 minutes for this. Uh, I didn't get what you meant, Sam. Uh, okay, so for the recording, Samar has written that using combi we can definitely find if we are going to win tetris or not. What is a tetri exactly? I see. Okay, so it's a game. I don't think that. Yeah, sure. Uh, I don't think that this will exactly help with this problem, but thanks for. Uh, I will search it. If anyone has any idea, just speak. If possible, then if otherwise. Any idea? Uh, if not, then you can say no so that I give a hint. So, okay, yeah. So, as we thought about in the past few strategies, it's still nice to think of the chessboard color. So you could consider coloring this like a chessboard, and then think about the kinds of determinants you would have based on which squares they cover. Does that help? Okay. So I'll just repeat what I said. Uh, okay, I'll rephrase what I said. So you color this ten board like a chessboard. Is that fine? So you color it. Okay. So you color it like a chessboard, and then try to tile it with some t determinants, and then see what each t determinant, which squares each t determinant covers. Did that make sense?
Yeah, I think I got the proof.
Yes. Go on.
So like we can color the chessboard by checkerboard. Each T tetromino covers exactly 3 of one color and 1 of other color.
Exactly.
And there are 25 tetrominos and equal number of black and white squares. So that's a contradiction.
Wait. Can you repeat the last part?
So there are 25 tetrominos we will require.
Yeah.
And there are equal number of black and white squares. So the last tetromino cannot cover equal number of black and white squares.
Okay. Yeah. I guess. Yeah. It works. Uh, just to formalize that a little more. I guess formalize. Maybe your works perfectly as well. This is just new, a bit new. So if there's a x of the type 3 white and 1 black for each t determinant, and y of the type 3 black and 1 white, then we have that x plus y is 25 because the total number of t determinants has to be 25, and 3x plus y is equal to 50. So if you subtract the two, then you have does everyone have a paper and pen, or is this just going over the? Yeah, I hope that you people are writing this or something because it won't make sense otherwise. So x plus y is 25 and 3x plus y is 50. You subtract the two, you get 2x is equal to 25, and uh, that's obviously a contradiction because x is an integer. Arnav, was this almost the same as your proof?
Yes, I think so.
Yeah. Did everyone get this? I assume yes. If anyone has any question, please speak up or write in the chat. I'll be here. So the main point here was to try writing out trivial stuff, like trivial algebra before giving up on coloring. It's not just in a coloring problem, we just don't want to color and then give up because you can't think of anything else and go on to some other coloring. Sometimes you want to write trivial algebra, basic algebra to get things done. By the way, the last problem has many other approaches as well. Uh, including non-checkerboard coloring stuff. And please, I encourage everyone to try this. Try to think of more methods. Uh, was the problem and this strategy uh, clear and understandable to everyone? Uh, yeah, so I think this is either it's very similar to in more 2019 or 20, I'm not sure, P6, or it's exactly the same, I'm not sure. But do try this. It's a very nice one. But I think it was pretty standard before. I mean, it was known before the Enmo happened, and their solution doesn't use coloring. I think the official solution. They use complex numbers and things, but I guess that's in general complex most coloring questions, tiling questions can be solved using complex numbers. Uh, I find it nicer to find a coloring instead. It's almost the same thing. I guess it can be translated. Corner points. Okay. So Samar claims that the positions of the unit squares must be this, or this. Okay. Can everyone see my cursor? Uh, can you guys see my cursor? Yeah. So this Summer claims that it's this, this, or this. So first of all, do you have a construction for how this works? How this could work? So you did this on a 4x4 board, and you set this for an 8x8 board. Okay, it's a very nice tactic to think about small cases, and it's a very important idea as well. So I haven't tried the 4x4 case exactly, but generally when you are, I mean, I don't exactly have examples of when induction kind of arguments work for coloring problems, but maybe they could. It's anyway a nice idea. You should think about such things and try several small cases. But I guess it's important to try several small cases. So you tried 4x4, and you're considering it for 8x8, but I guess it helps to try out 2x2, 1x1 maybe. I mean, it's trivial, but then 3x3, just try some random cases. And lastly, you need to find a construction for it, for the conjecture first. That would really help. Yeah, okay, yeah. Now I see how for 4x4, yeah, it does work. For example, if you just look at this one, then if this one is covered, I mean, this one is tiled with the one unit square, then yeah, this, and this, yeah, it works for 4x4. So I'll just spoil this. It doesn't work for 8x2. I mean, you could try tiling it like that, but it just doesn't work for any possible case. Uh, and it's actually very important to understand it logically. It's not that we are exhausting all the for proving this. We can't just exhaust all the cases for when it's uh, on one of the corner squares. When the unit square will be on a corner square, then you can't just exhaust all the possibilities by doing 1 into 3 tiles. But that's impossible to do for a human hand in contest timings. So you need to find an actual proof for it. You can't give an example and leave it there. So counter examples work, but obviously just examples won't work. So the corner square doesn't work, and I'll give the proof using coloring uh, later when you guys are done time. Uh, I guess I'll give around 5 more minutes. I'm just speeding things up because I have another half of the lecture to uh, do, and this presentation is still not over. If it's too fast, then you can just tell me to slow down and give more time for each problem. Uh, okay, so Samal has a conjecture. Uh, it's uh, that I guess is this the yeah. So he says that the unit square might have been should be on one of these four, the middle four squares, the middle two and two squares. Sorry, but I'll have to spoil this again. It doesn't work. It's a nice idea though, but I would suggest that like it's a hint. Do people want me to give a small hint now, or should I wait? Uh, wait. Answer. Uh, wait. Answer. Am I audible? I guess I'm not to some. Okay. Can you hear me?
Yes, we can hear you.
Okay. So did you hear me when I said? Okay. I'll just repeat it. So Samuel conjectured that this 2 into 2 square is the answer. The possible position is this, or this possible positions. So I spoiled that and said that it doesn't work. And I was asking if I should give a small hint here, especially to the approach that we were using. Can I do that? Am I audible or am I gone again?
I've got that the four squares on the diagonals work. The
Four squares on the diagonal. So you have this diagonal and
third from the corners.
third from the corner. So
Those four. Like
this,
not
and this.
only those, but those four minimum work.
Minimum. Is that the minimum or it's the maximum?
It is the minimum. Like I got at these four work. Not sure about anything else.
Uh, uh, so can I give us like I'll just tell this. That's actually exactly the solution. The solution set. Um, but the point is that how did you get that? In? Did you just experiment it?
Yeah, experimental.
Okay, super nice. I mean, that is really quick in some sense because you had 64 squares to try. Uh, so it does work, but the point is that that's exactly the solution set. And but you need to give a proof of why that's why nothing else works. And you already show that that works. Now you have to show that nothing else works. Later, I'll get to how you can, without doing too much experimentation, just figure out that this actually that will just be the same. Uh, so, does anyone? So, since we are in a coloring class, we are going to color. So, does anyone have an idea of how we are going to color this board? Uh, any just give any ideas. You don't need to be right. I mean, most probably anyone who's seeing this for the first time is going to be wrong, especially the way I have approached this. So maybe the first idea you might be having is doing a checkerboard coloring again, chessboard, I see chess. So wait, can we use induction coloring problems? Sure, you can. You can do induction wherever you want, but I have no examples of where that might be useful. And for this problem, especially, first of all, if you're using induction, you're probably not going to use coloring, I think. Has anyone seen a problem where induction helps? Yeah, so
I think induction might help in showing that such a construction is possible.
wait, how?
Like sometimes.
Okay, yeah, in general cases, yes. Over here, I guess there's no use of induction. Did you use induction to show that the four squares that you said work?
No, I constructed.
Yeah, so here, okay, so you tried up one problem a month ago in the induction class. I didn't do the induction class. Was that a coloring problem? It was a combi problem. Yeah, so induction obviously does help. It helps everywhere almost. It helps in constructions. Okay, I just can't list them. It's a box problem specific. Original principle. Oh, okay. So, like spoilers, induction doesn't help here. Uh, at least I don't know of a way that. Maybe you could try starting with 4 into 4 and then going to 5 into 5, but I don't see any way to correlate the two. Uh, so, anyway, since we are in a coloring class, we should probably try to color this 8 into 8 board somehow. The first idea, since I've been talking about this for most of the part, most of the talk till now, that we could do a chessboard coloring, but you would notice you could type. I haven't personally. I haven't done that personally, but it's not very natural to do that with a 3 into 1 square. It's not even an even numbered type. So you could try looking at it mod 3 sort of. So the idea here is that you could try coloring this with 3 colors. Uh, did everyone get the idea?
I tried that, but I didn't get how do you reach to those four squares? Because the same color would
Yeah,
be used many times.
exactly. The problem is actually that's why it's in move p6, I guess. It's pretty nice. The thing is that here it's not the only step to just in till now what we have seen is we color and then it's either trivial algebra or some it's very trivial after that and the coloring just finishes the problem. But here it's a bit deeper than that. It still involves a bit more coloring, but it's not over there. So nice idea of trying 3 colors. So we'll still try to follow our nose and continue with that. So the strategy was to that each tile covers 1 square of each color. So for example, over here, if you had 1 into 4 tiles, then you would color it with 4 colors. So something like that. This has been fruitful in the past for us when we thought of the chessboard coloring problem in some sense. Yeah,
I think
very
using the coloring, we directly get that like the color which should be left out.
yes.
And the four colors of four squares are the same color. Yes.
So okay, Samar, I'll get back to that sometime. One second. So you have two possible colorings actually. interestingly. So it's obvious that if you color this red, and that's without loss of generality. So if you color this red, then this is either green or blue, and without loss of generality, green. So wait, yeah. So this is red, this is green, and this has to be blue because each 1 into 3 tile covers 3 tiles of different colors, 3 squares of different colors. Then this has to be red, then this green, then blue, then red, then green. But here you have two choices. You can either have this green or you can have this blue. So once you have this, the rest of the board is unique. Does everyone see how? Am I audible?
Yes, you are audible.
Yeah. So do you see how if
Yes.
this, yeah, so if this square is either green or blue, so if this is done, then it's uniquely you can uniquely identify the entire board. So rather than just sticking to one of them and trying to continue with that, I guess it helps to just it's just two cases, so there's no problem in writing them both out. So you have this grid and this grid. So you can just count the number of red squares here, the blue squares here, and the green squares here. And I guess it's pretty easy to notice that the number of green squares is the most in the left diagram. Can you see how? I mean, just counting. Uh, is that clear? Like the number of green squares in
Yes.
the, yeah. So the number of green squares is the most in the left, and in the right, the number of red squares is the most. Is that fine? Yeah. So in the left one, the number of green squares is the most, and in the right one, it's the red. The number of red ones is the most. So it's clear that the unit square has to be on the green square here and on the red square here, right? Because each 1 into 3 tile covers exactly the same number of green, blue, and red squares. So the extra tile in the green squares in the left side and in the right side the red square, it has to be the 1 into 1 tile. It can't be covered inside the 1 into 3 tiles. Is that fine? I can explain it explain it more rigorously if it's not.
Yeah, it's fine.
Okay. So it has to be on a green square here and a red square here. So now the magical idea, I guess, it's the crux. We add the colorings. So it's strategy first, we add coloring. So if we add the two colorings, then these four, the unit square has to be one of these four because it has to be the green in the left diagram and the right and red in the right diagram. So if you mix the two, it has to be in both the green of the left and the red of the right. So it has to be in the intersection. So it has to be one of the. I just made. I mean, it's not mine, but over here, red plus green equals yellow. Is this fine? So the unit square as yet Arnav had as Arnav had claimed, the yellow squares are the ones where the unit tile has to be placed. So I guess we approached it in a different way. So this comment doesn't make any sense. Easy to do that, I guess. Am I audible again? Internet problem.
Yes.
Yeah. So did everyone get how we ruled out all of the possibilities but these?
Yes, we use the correct conditions from both the tiling, both the colorings, and then reduce it down to those 4 squares.
Exactly. So these yellow ones are the important ones, and then we can just do the coloring. We can just style it that way to finish it. And also, you don't need to. I mean, uh, Arnav experimented and found that these four are the only ones possible. These ones do work, but you don't need to exactly do that. The coloring just directly works, and the coloring was like completely intuition based. I mean, the motivation to do the coloring was clear because you had three color, one tile, 1 into 3 tiles, and three colors were best. So uh, wait, I'll just get my charger. Give me 2 minutes. Yeah, sorry about that. So now for some maths. So this is probably the solution to the problem which you would see in a, book or something. Uh, so you number these. You can just take the original 8 into 8 square. Then you number it this way magically because they give no information. Then we have that each 1 into 3 tile covers the sum of, uh, covers the sum of exactly two. Is that clear? How that works?
Yes.
So and the sum of the entries is 44. Just add them up, and since each 1 into 3 tile covers a sum of exactly two, we have that obviously that since we have 21 1 into 3 tiles, the 1 into 3 tiles together cover a sum of 42. So the last tile, 1 into 1 tile, has to cover the sum of exactly two. So the four yellow squares are the ones which are. Did everyone get this? Uh, is the solution clear?
Yes, like it looks quite easy from what we did, but like it's not intuitive.
Yeah. From what we did, this can actually be a nice way to represent your work, so that you don't have to write. You don't have to explain adding up colors and stuff. So from our point of view, this is just a way to clean up our solution. But the if you see this in a book and we are just lost about how you would think about this, uh, so it's probably not a very nice way to think about the problem in the first place, but it's a pretty nice solution. It's math. So uh, this is a nice problem, but uh, should I cover this or should I move on to the second part of the lecture? It's on people's vote. I guess we won't have much time for the second half. It's fine. I guess I'll do this first. Uh, there are many methods to do this. Just give me whichever ideas you're able to think about. And I personally found I found three solutions to this, and two of them are verified using solutions that other people have done, and the third one I think it works, but I've not checked it from anywhere. I'll just give the two which are available from elsewhere. Also, I'll give the credits at the end. So just tell me whatever ideas you have anytime. I'll give about 2-3 minutes for this. Yeah, also one thing just for speeding up things. They have written a 13 into 13 chessboard, and sorry, but the chessboard coloring doesn't. So you have to try something different. And also the most natural thing to do, as in the last problem, would be to color the 4 into 1 like color it with 4 colors so that each 4 into 1 tile covers exactly one color of each type, of one square of each type. So that's the solution I found actually. I have not verified it from anywhere else. So uh, I guess think about the difference. Just give me ideas as soon as you get. Yeah, and also someone had written something like, yeah, I got the problem as well. It was 2 to the power 100 into 2 to the power 100. Oh, the induction question. Somehow it was the induction. Yeah, I love that problem actually. It's that I guess you remove a cell and then show that it can be tiled with terminals. So yeah, you divide it into 4 different squares, and each square, I mean, you divide it through the center line and you have 4 different squares, and then you remove one cell from each, then uh, I guess after that it's easy after that. Uh, the one tile has to be in one of the 4 smaller squares. The the removed cell. So the removed cell has to be in one of the 4 smaller squares, and so after that it's just obvious because you can tile it uh, otherwise. That was a very nice problem. Yeah, so that was a tiling problem. That is, yeah, it's a nice example. Uh, but the point is that the question was a construction, and here the approach we used was more like destruction. We showed that some things are not possible. Yeah, but nice example. I'll give it in the general chat if you don't mind. It's a nice problem if people want it directly. I actually thought about putting this in this lecture, but it is not a coloring problem. So uh, I guess it's pretty famous. Is this, yeah, Samara, was it fine? I posted it in the general. Uh, yeah, that problem was like 2 to the power n into power n board. And you want to show that if you remove one cell, then it can be tiled with prominence. That's a different problem, but it's nice. It's induction. Yeah. So any ideas on this one? Uh, okay. I guess I'll show the coloring and then, or maybe, yeah. I guess the intuition comes from the fact that the chessboard coloring doesn't work because that gives you what you would need from the coloring so that it does work. Uh, I mean, that's the first solution that was given. So this is the new board, not chessboard coloring, but close enough. It's 2 color. So each 1 into 4 tile covers 2 squares of the same color. You can place them anywhere and check. So the if you remove one of the tiles, then after this, it's pretty clear after this. So if you remove this, the center square is, I think, white, but the black squares are more.
Answer to most of the like, is it possible problems is no, right? Like in many problems.
Uh, I guess for color, if the problem can be solved using coloring, yes. But in general, I guess Paul Zeitz wrote on this in his book. So in general, try to hope that it's true, and just try it out. See if it doesn't work, then you'll almost immediately see it by trying out a few cases. But yeah, I guess in general for tiling problems, it doesn't work. I mean, the
Hmm.
answer is no.
Yeah.
I guess nice counter example to my claim is the problem that Samar said. I guess if the question was can we tile it or not, then it would have been a bit harder because it's not very clear how you would directly approach it. Maybe you could try smaller and um, see whether it actually works or not. Then try it. Yeah. But in general, for tiling problems, the answer is no. If it can be solved by color. So, uh, is this solution clear? I'll assume yes. If any problem, then just message or speak up as usual. So this is the second solution. It requires a bit more intuition, but I guess the main point is that you use 4 colors instead of 2 because you have a 1 into 4 type. So you color this whole thing green, then this black, then this white, red, green, black, white, red, green, black, white, red. So uh, the number of uh, the center square is white, but each 1 into 4 tile either covers square of each type, or it covers all 4 squares of the same type. In either case, the difference in the number of squares covered with white, number of white squares covered, and the number of uh, black squares covered has to be a multiple of 4. Either it's 0 or it's 4. But if we are going to remove the center square, then we are removing a white square. So does everyone see how that's a contradiction? If you don't see it immediately, you can just tell. Uh, this is basically just me treating the solutions. Yeah. Yeah. So yeah, I can repeat it. The each 1 into 4 tile covers either 1 square of each type, or it covers all 4 squares of the same. Because if it's placed vertically, then it's all 4 squares of the same type, and if it's placed horizontally, it has to be So in that case, the number of white squares covered by the 1 into 4 tiles minus the number of black squares covered has to be a multiple of 4. Is that clear? Uh, uh, okay, yeah. This is uh, this. Just a second, Martin. I'll just explain the solution first. So if it's like uh, let's see, yeah. So in the case when the 1 into 4 tile is placed horizontally, you can see that 1 square of each type is covered. So number of black squares covered is equal to number of white squares covered for those tiles. And for the other type of tiles, either there is no white square or black square covered, or there is only white squares covered, or there is only black squares covered. And the number of, so the difference is always 0 mod 4. Yeah. So now is it clear? Okay. So so Martin's question was, does alternating rings of squares work? If outermost is black ring, then we have uh, 90 more black squares, which is 2 mod 4, but it must be 0 mod. 90 more black squares, which is 2 mod 4. What does that mean exactly? If you could be, wait, so you say, yeah, 90 is 2 mod 4. 90 more black squares. So yeah, okay, yeah, uh, that should work. Wait, alternating rings of squares. So alternating rings of squares, do you mean this whole thing is the outermost layer is black, then the second is white? Yeah. So how many colors are these? Okay. So it's the outermost layer is black, then white, then black. Yeah, I guess once. Yeah, black, white, black. So on, and the center square will be, I guess, black, white, black, white, black, white, black. So the center square is black. Uh, and if you remove the center square, then you have equal number of. How do you get the contradiction? Uh, Martin, how did you get the contradiction again? 2 mod 4, 0 mod 4. I didn't get it. 90 more. Wait. Uh, so you have 90 more black squares applied. Okay, so you counted the number of black squares and the white squares, and you found that there are 90 more black squares. Yeah, here's it. Like each 4 into 1 tile is either all black squares or all white squares or 2 black, 2 white. Wait, let me check this again. Yeah, obviously. So, oh yeah, so the difference has to be 0 mod 4, but he calculated and found that there are 90 more black squares than white squares. That is 2 mod 4, but it should be 0 mod 4. So that's a contradiction. Nice solution. Do you want to tell, if you feel like it, how you thought of the coloring?
Um, I thought of like making the 4 by 1 tile like a multiple of 4, like difference of black and white. And then like if
Uh,
you put random like 4 by 1 tiles, then like
yeah,
I think the squares coloring is only one of them. There can be other ones also.
yeah, yeah. That is good intuition. That is exactly the same intuition as we used in the second coloring except, right?
Yeah.
Yeah. So, uh, yeah, nice solution.
Thank you.
Uh, no, uh, so that was part one of my lecture, but I've almost exhausted all of my time. But I guess we can look at a couple problems from the general combinatorics as well. Uh, so I really like this problem. It's I've written here as yeah, I'll cut this. So the yeah, so it relates to a larger problem. It's the Hadwiger-Nelson coloring. It's still an open problem. So this is like a very tiny, easy case of. So you can, I guess I'll, yeah. So I suppose that it's not very nice to leave you with this problem because uh, it's it's nicer as a group solve. Uh, so what you just play with the things. Whenever you have a problem with just random things like this, it's like a process. Then you just play with it. Uh, so we have red, green, and blue, but I guess I have black, red, and what's black, red, and purple. Uh, so I'll use black, red, and purple for red, green, and blue. Uh, so suppose this point is red, and you have something 1 unit away. The first thing is that we proceed with contradiction because you need to show that there exists. Oh yeah, did everyone get the problem statement first? Am I audible? Uh,
Yeah, we are audible.
okay. So the problem statement is that clear? Uh, I assume yes. Uh, so uh, Suppose that this point is colored red, then 1 unit away, everything is either red or it's either green or blue, or in my case, blue or black.
So are you showing anything on the screen? We can see a blank slide.
Oh, right. 1 second. I'll have to share again. Can you see it now?
Yeah.
Uh, that's why I was asking if the problem statement is clear. So can everyone see the problem? Problem one.
Yeah.
Uh, so in the question we have that every point in the plane is colored with 3 colors, red, green, or blue. We need to show that there exist 2 points of the same color that have 1 unit apart. Did everyone get the problem? Yeah. The natural thing to do here is to proceed with contradiction because what we do is we assume that uh, there exist there don't exist 2 points of the same color that are 1 unit apart, and that any 2 points, that is equivalent to saying that any 2 points which are 1 unit apart are of different colors, right? Does everyone see how that works? Okay. Everyone is following. Okay. I'll just assume. So suppose this is 1 unit apart, that is this distance is 1. Then and also that we'll basically construct a hexagon. So this is also 1 and this is also 1. So this is an equilateral triangle. Just assume that it is. My drawing skills are bad. Then this is also one. This is one. This is also an equilateral triangle. This one, the lower triangle. And then this has to be black, right? If this is also 1 unit apart. Am I drawing? Yeah. What's wrong? So this is this is blue, and this has to be black. Did everyone get this? Yeah, bye Saman. Thanks for attending. So this is red, then these three are purple, and these three are black, right? This is just a regular hexagon of side length 1. Does everyone get this?
Yes.
So since we are proceeding with contradiction, let's try to. So, any chance anyone seeing a contradiction here? Like immediately, anything which is jumping out, possibly. Yeah. So there isn't, at least to my eyes, there isn't a direct contradiction here. So the point is, as my quote says here from Remus Nicola, that we just follow the same strategy. We continue playing with it. Then this has to be red, right? Because this is again 1 unit. Most of the stuff is either 1 unit or 3 units. This is 1 unit. This whole thing is an equilateral unit length triangle. Then, so this has to be red. It can't be blue, it can't be black, it has to be red. Similarly, this also has to be red. Then this has to be red. This also has to be red. This has to be red. This has to be red. Right? Does everyone get this? Did everyone get this part? How these 1, 2, 3, 4. These 6 outer points are red. Okay, I'll assume yes. Can anyone tell me what this distance is? So I just marked out some things. This is 1. How do you erase this? This is also 1. Can you tell me what this distance is? It's just basic trigonometry. This is 120 degrees if I need to mark it. I mean, this is just the reflection of this over this. This was the reflection of this over this. So this is how many degrees? Anyone? It's 120, right? Because there are two equilateral triangles. 60 plus 60 is 120. Is everyone following this, or should I repeat anything?
It's root 3, right?
Yeah, exactly. So this is root 3. So this is root 3, and then similarly, this is also root 3. Is that true? So all of these red points are the farther red points are root 3 away. So this whole thing is like root 3. Does everyone? So my claim is that this whole circle is actually red. All these points have to be red. And you can see this by just rotating the smaller hexagon we just drew over the whole circle. Then all the points on the root 3 radius circle with center as the red point have to be red. Does everyone get this?
Yes.
So this whole thing is red. So now does anyone see a contradiction? I actually
Yes, in the circle there must like 2 red points which are 1 unit apart, right?
exactly. So there are 2 red points on this circle, 1 unit apart, and these give a contradiction. So we are done. Does everyone? Okay. Did you get the proof? So I was shown a different. I mean, this is the proof I knew, and then I had done the approximately the same talk somewhere else, and they had shown me a different solution. So if we consider this purple point here, then that also has a root 3 radius circle about it. And if we draw that, it has to intersect the red circle in 2 points. And so this says that these points, the intersections, are both blue and red. And it can't be green or something. I don't know what blue plus green. I guess it's black. Indeed. So it can't be both blue and red, so that's a contradiction. Did everyone understand the second proof? Did anyone understand the second proof?
Yes.
Uh, so that is the first problem. I guess we can try the second one for some time. If let's see how much time we have. So this was mainly for helping people who like geometry here, because I didn't do anything. I wrote a very elementary geometry as a prerequisite and haven't really done anything much. Maybe this problem had a bit of trigonometry. So second problem. Can everyone see the problem?
Yeah.
So if once you're done reading the problem, just tell me. Just read and say done or something.
Yeah.
Okay. So can anyone tell me like what should be the approach in this problem? It's basically the same as the same approach as problem one. Not the playing part. Like what should we do concretely? Like induction, construction, something.
Contradiction.
Yeah. So we use contradiction here again, and we assume that any triangle which we form has doesn't have is not monochromatic. Does everyone? I guess it's clear. So if we do draw a triangle, then what can it be? It can be red, blue, blue, or blue, red, red, right? Is that clear?
Yeah.
Yeah. So this is red. Then I'll just say that this is alpha, beta, gamma without. So this is red. This is blue. Then this is blue. This is without losses. I mean, I'm just drawing a case. Doesn't matter. So this is our first triangle. Now, so this is probably a bit hard. The second part. Okay, so colors mix over. Sadly. So which other triangles related to this triangle have angles alpha, beta, and gamma?
Like the medial triangle, probably.
Yes, very good. Like very nice idea. So, by the way, any other ideas?
Reflection may be like looked at the top vertex.
Malay, do you know the solution to this one? Or,
No, I did not know.
okay. So yeah, that is another important triangle. we don't know whether that works yet or not. So this is the second triangle. I'll just mark these points black for now. Since we don't know whether they're red or we'll talk about that now. So this is we can just reflect this red point over we could reflect the blue points as well, but it's more symmetric to reflect the red point, right? So we reflect the red point and we get this new triangle. So I'll just mark the points. This is D, E, and F. This is ABC. And this is G. So do we know anything about what the colors D, F should be? Like anything.
E should be red.
E should be red. Yes. How did you? It's
Because
correct.
D and E cannot both be red. So one of D and E has to be blue, and considering that corresponding vertex, you get E has to be red.
Correct, but I think you meant F when you said E the second time.
Oh yes, sorry. D and at least one of D and F have to be blue.
Yes. So if both of these are red, then we have a monochromatic red triangle, which has angles alpha, beta, and gamma. So that's a contradiction. So one of these has to be blue. So without loss of generality, D is blue. It really doesn't point. So if D is blue, then triangle BDE is also similar to triangle ABC and has angles alpha, beta, and gamma. So if E is blue, then that's a contradiction because you would have a monochromatic triangle with angles alpha, beta, and gamma. So E has to be red. Does everyone see how, in general, if line X and Y, line XY is if point X is blue, point Y is blue, then the midpoint of line XY has to be red. Does everyone see that? Because using any line, we can find a triangle which would give us. I mean, if this were X and this were Y, then you can still find an Z, say, which would have this thing, like A to B and C. Is this clear?
Yep. I see
So,
the solution.
By the way, this is a bit of a digression, but do we know anything about F over here? Like whether it's red or blue? No, right?
I don't think so.
Yeah, we don't know anything about F, so just ignore it. Now
We can say that G is blue.
yes.
Oh no, yes, we get a contradiction.
Yeah. So I guess I was about to ask, what's the color of G? Then I expected to hear some reds and some blues, but we just found a contradiction. So E is the midpoint of AG. So G has to be blue, right? Because this is red, so this has to be like we just said, the midpoint of any. If this were red, then the midpoint has to be blue, but that's not the case. So now triangle BCG, that's all blue, and it has angles alpha, beta, and gamma. So that's a contradiction.
Yeah, this was nice.
Yeah. So that was the. Did everyone get the solution? I suppose yes. This is one of my favorite problems in coloring. I mean, it uses very simple things, but it's important to keep thinking of more ideas instead of like what I did in the problem was I thought of the medial triangles first, and then I got stuck over there. I spent a lot of time just trying to think about how this medial triangle could solve the problem. But if you just reflect A over E, then we have another similar triangle. So in general, just keep, there's no point in just sticking to one idea for a whole lot of time. So just keep adding more ideas as you find them, and keep following your nose. Don't don't lose the ideas at some point because you think that one idea would work, but the other won't, and you go back to the first one, and you go back to you do the one which you think which will work, but that doesn't seem to work. Then do try the other ideas rather than just eating up the solutions. So I guess I'm over time now, so I won't get to do the other problems. I can share the wait. I don't want to do. What should I do?
Do you want to stop screen sharing or something?
No. Yeah, sure. I guess. No, I wanted to move this a bit. Yeah.
Oh, probably, yeah, select.
Yeah. Yeah. I can share these other problems. These three. So the last two ones are. Malay, I was allowed to share this. Right?
Yeah,
So
yeah, it's fine.
yeah. So the last two ones are from the Sophie preset, and they're actually the last one is related to coloring. The problem 4 is not related to coloring, and I didn't get the solution. Malay told me this. Rishal told me the solution. It's a really nice problem. It doesn't involve coloring, but it will be nice if you can try it out. The third problem is it's actually pretty easy. It has a bit of a red herring. So what? So I guess we can stop the recording.
Okay, stop. Thank you for the class.